Good morning, all of you. So today we are going to discuss some basic concepts of chemistry, lecture 3, and the topic is mole concept and stoichiometric calculations. Very, very important topic. From this topic, definitely you are going to get questions for competitive exams. So mole concept and stoichiometric calculations. So coming to mole concept and stoichiometric calculations. So what is mole concept? So straight away already I discussed in terms of mole that a mole is represented as quantity, just like 1 dozen is equal to 12. So mole is represented as quantity, and in chemistry the amount of substance is measured in terms of moles. The amount of substance is measured in terms of mole. Now what is mole concept we'll discuss now. So what is mole? I hope you all understood. 1 mole of a substance represents quantity. So to measure the amount of substance in chemical calculations or chemistry, to measure the amount of substances, we'll use moles. So mole represent quantity just like dozen. And 1 mole of a substance contains Avogadro number of particles. 1 mole of any substance contains Avogadro number of particles. Now, what is Avogadro number? It is equal to 6.023 10 to the power of 23. 6.023 10 to the power of 23. This is called Avogadro number, Avogadro number and Avogadro number of particles. Now coming to mole concept, I'll write the mole concept in simple one line so that you can understand it's better. It's very, very easy to understand. So what are the conversions we have to do, that also we'll discuss today, and stoichiometric calculations. So coming to mole concept, I'm writing here the diagram. Please see the diagram. Mole it is equal to, it contains Avogadro number of particles, Avogadro number of particles. Also, it is equal to gram molar volume at STP. At STP is important here. At STP, where STP is called standard temperature and pressure. And mole is also equal to gram molecular weight. Gram molecular weight or gram atomic weight. So now I'm evaluating all these things. So mole is equal to Avogadro number. Mole is also equal to gram molar volume at STP for any gas, and mole is equal to gram molecular weight. So gram molecular weight is equal to, so for all this we can say equivalent to. So this is only mole concept diagram. So or if you note down mole concept diagram, so mole concept is nothing but 1 mole is equal to Avogadro number, 1 mole is equal to gram molecular weight, 1 mole is equal to gram molar volume at STP. And how to apply the concept for this, I'm just writing one more statement. So you can see in another slide. So next statement, 1 mole of any substance condition number 1 occupies, point number 1 occupies 22.4 liters at STP. Suppose if the substance is gas, it occupies 22.4 liters at STP. At STP, that is standard temperature and pressure. So standard temperature is 273 kelvins or 0 degrees C, and pressure is 1 atmosphere. Next, second point, 1 mole contains, 1 mole of any substance contains, second point, 1 mole of any substance contains Avogadro number of particles in it. Avogadro number, that is N of A, are particles in it. Particles in it. Point number 3, that is 1 mole of any substance contains, it is equal to its gram molecular weight. 1 mole of any substance is equal to its equal to its gram molecular weight. Gram molecular weight. So this is called mole concept in writing pattern. So 1 mole of a substance, 1 mole of any substance occupies 22.4 liters at STP. If the substance is made up of gas molecules only, we can write volume and contains Avogadro number of particles in it and equal to its gram molecular weight or gram atomic weight. Suppose if you take 1 mole of atom, it is equal to its atomic weight. Now applying mole concept, for example, 1 mole of carbon dioxide, 1 mole of carbon dioxide gas. Okay, point number 1 occupies 22.4 liters at STP. I'm applying mole concept. How to write mole concept for a given statement at STP. Point number 2 contains 6.023 10 to the power of 23 carbon dioxide molecules. 6.023 into 10 to the power of 23 carbon dioxide molecules. Because we have taken carbon dioxide as a molecule, we have taken carbon dioxide molecule. Example, I'm applying mole concept to carbon dioxide. Third point, 1 mole of carbon dioxide is equal to. So what is the molecular mass of carbon dioxide? In the previous session, we have discussed how to calculate molecular weight of carbon, any molecule. So carbon is 12, oxygen is 16. So 16 into 2, 32. So total it is 44 grams. So if the molecular weight is expressed in grams, it is called gram molecular weight. So 1 mole of carbon dioxide occupies 22.4 liters at STP, contains 6.023 10 to the power 23 carbon dioxide molecules and is equal to carbon dioxide. Weight is how much? 44 grams. So this is called application of mole concept. And fourth point in this, we can write one more point add to this. 1 mole of carbon dioxide contains 3 into Avogadro number of atoms present in it. Atoms present in it. So how this concept came? For example, carbon dioxide is a molecule consisting of 1 carbon atom and 2 oxygen atoms. So 1 carbon atom, 2 oxygen atoms. So together it is total 3. So 3 into Avogadro number of atoms present in it. If they ask 1 mole of carbon dioxide contains how many atoms in it, means we have to write 3 into Avogadro number of atoms in it, or 3 into Avogadro number of particles in it. If they ask 1 mole of carbon dioxide contains how many molecules in it, we can write just Avogadro number of molecules in it. So in this way, we'll write for carbon dioxide. So I have applied the concept in the case of carbon dioxide. This is called mole concept. Now, in the coming session, now we'll do the problems related to mole concept. That is, questions related to mole concept. Problems on mole concept. So, problems on mole concept. Right heading. Problems on mole concept. We'll do all the different models. Model number 1. Question number 1. Which of the following weighs more? WEIGHS. Weighs more. Question mark. Option 1. First option. 2 grams of hydrogen atoms. 2 grams of hydrogen atom, hydrogen molecule, 2 grams of hydrogen molecule. Option 2, 56 grams of iron. Option 3, 8 grams of helium. Option 4, 32 grams of sulfur. So these are 4 different options they have given. So out of this, how to find which of the following weighs more? These type of questions are most important for comparative. So now I'm doing the solution for this. Just you can see here, this is model number 1, solution. So which of the following weighs more? So by seeing the weight, we can say simply 56 grams of iron is more, but that is not the right answer. So whenever this question has come, we have to convert the given weight into number of moles, and whichever is having number of moles more, that is having maximum weight, because more, this is called mole concept. And we have to, in chemistry, weight is not weight is to be considered as amount of substance is to be considered with moles. So let us verify first option, 2 grams of helium hydrogen molecule. So 2 grams of hydrogen molecule means it is equal to the molecular weight of hydrogen is 2. So 2 grams of hydrogen molecule is equal to, so it contains molecular weight of hydrogen is 2. So it is equal to 1 mole. Is equal to 1 mole. Because the molecular weight of hydrogen molecule is 2. So it is equal to 1 mole. Next, second option, 56 grams of iron. Iron is monoatomic element. So 56 grams means it is equal to its gram atomic weight. So 1 mole is equal to gram atomic weight of iron. So 56 grams of iron contains 56 grams of iron contains also equal to 1 mole. That is 1 mole. Next, third one. So we have to convert the given weights into moles. Third one also, third option I am verifying, 8 grams of helium. So you know helium is monoatomic molecule. So 8 grams of helium contains, 4 grams of helium is 1 mole. 4 grams of helium is equal to 1 mole because the atomic weight of helium is 4. So 8 grams is equal to 2 moles. So for third option, this number of moles is equal to 2 moles. And fourth option, 32 grams of sulfur. 32 grams of sulfur. So it is equal to, so the atomic weight of sulfur is equal to 32. So it is equal to 1 mole. So equal to 1 mole. Now, first option is 1 mole. Second option is 1 mole. Third option is 2 moles. Fourth option is 1 mole. So which of the following weighs more is the answer is third option, that is 8 grams of helium, because it is equal to 2 moles. So 2 moles means it contains 2 into Avogadro number of particles. So this is question number 1, model number 1. Very, very important. I hope you understood. So 8 grams of helium is the answer. So again, I'm repeating the question. Which of the following weighs more? 2 grams of hydrogen molecule, 56 grams of iron, 8 grams of helium, 32 grams of sulfur. So they are given individual molecules and atoms. So hydrogen exists as diatomic molecule. That's why they are given hydrogen molecule. And iron is given as atom, and helium is atom, and sulfur is also atom. So that's why by giving the, we have to convert the weights into moles. So this is the model which represents weight to mole. So weight to mole. So 2 grams of hydrogen molecule is 1 mole. 56 grams of iron contains 1 mole. 8 grams of helium contains 2 moles. 32 grams of sulfur contains 1 mole. So generally the students will do, answer is 56 grams of iron, they will think, because it's having more weight. But in chemistry, we'll consider weight with respect to moles. We'll not consider weight with respect to grams. So our answer is third option, 8 grams of helium, because it contains 2 moles. So that is the answer. So this is model number 1. Next, model number 2. Question number 2. Which of the following contains, which of the following contains maximum number of which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum number of particles? Which of the following contains maximum maximum number of particles. This is second important model. You can see the previous year's questions also. You'll find this type of questions. So which of the following contains maximum number of particles? Option 1, option 1, 22 grams of carbon dioxide molecule, 22 grams of CO2. Option 2, option 2, 17 grams of ammonia, NH3. Option 3, option 3, 49 grams of sulfuric acid, H2SO4. Option 4, 32 grams of sulfur dioxide. So they'll give which of the following contains maximum number of particles. These are the 4 different options. So how to solve this type of questions? First, we need to convert the given weight into number of moles as well as number of particles. So first option I'm solving, you can just see. So first take 22 grams of carbon dioxide, and which of the following contains maximum number means which of them contain maximum number of moles is called answer. So for 22 grams of carbon dioxide, we know 44 grams of carbon dioxide is 1 mole. 44 grams of carbon dioxide is equal to 1 mole, and they have given number of particles. So in carbon dioxide we have 3 particles, that is 3 atoms, that is 1 carbon and 2 oxygen. So it is equal to 3 into Avogadro number of particles. The answer is 3 into Avogadro number of particles. That is first option. But here the question is 22 grams. So 3 by 2 into Avogadro number of particles. So simply I am writing here 3 by 2. 3 by 2 by 2. So answer is 1.5 into Avogadro number of particles. That is solution 1. Now option 2. Verify option 2. Option, because they have given 22 grams, 44.2 grams is 44 grams of carbon dioxide is 1 mole. So 22 grams is 1 by 2 mole. So 1 by 2 into 3 into Avogadro number of particles. So it is 3 by 2 into Avogadro number of particles. Now similarly we verify option 2, 17 grams of ammonia. So we know molecular weight of ammonia is 17, nitrogen 14, hydrogen 3, 17. So 17 grams of ammonia contains 17 grams of ammonia is equal to, so number of atoms is equal to 4. So 4 into Avogadro number of particles. So what is the answer? 4 into Avogadro number, because one nitrogen, 3 hydrogen atoms, 4 into Avogadro number. Similarly, option 3. Option 3, 49 grams of sulfuric acid. We know 98 grams of sulfuric acid is 1 mole, because the molecular weight of sulfuric acid is 98 grams. H2SO4 molecular weight is equal to 98 grams. 49 grams is equal to 0.5 moles. 1 by 2 moles into number of atoms in sulfuric acid, 2 hydrogens, 1 sulfur, 4 oxygens. So 2 plus 1, 3, 3 plus 4, 7. So 1 by 2 into 7 moles. 1 by 2 into 7 into Avogadro number of particles. Next, fourth option, 32 grams of sulfur dioxide. You know, sulfur dioxide molecular weight is 64. So 32 grams is half mole. So for sulfur dioxide, answer is equal to 0.5, 1 by 2 into Avogadro number into 1 by 2 into Avogadro number, that is number of particles, and 1 plus 2, 3 atoms. So 3 by 2 into Avogadro number. So now answer is clear for you. So we have first option is 3 by 2 into Avogadro number. Second option is 4 into Avogadro number. Third option is 7 by 2 into Avogadro number. And fourth option is 6 into 3 by 2 into Avogadro number. So what is the answer now? 4 into Avogadro number of particles, because 1 by 2 into 7 is 7 by 2 is 3.5. So 1 by 2 into 3 is 1.5. So answer is 17 grams of ammonia will contain maximum number of particles. So in this way you have to calculate. 17 grams of ammonia contains maximum number of particles. Again I repeat the question. Which of the following contains maximum number of particles? To get maximum number of particles, we have to consider the weight of the given molecule and also the number of atoms present in it. Also, the number of atoms present in it is most important. So, for example, in 22 grams of carbon dioxide, already we know 44 grams of carbon dioxide is equal to 1 mole. So, 22 grams means 1 by 2 mole. So, 1 by 2 into number of atoms in carbon dioxide is 3 atoms because 1 carbon, 2 oxygens. So, it is total 3 atoms. And it contains Avogadro number of particles. So, 1 mole contains Avogadro number means 1 by 2 mole contains N by Na by 2 into 3. So answer is 1.5 into Avogadro number of particles. The same way we'll find for ammonia and we'll find for sulfuric acid and we'll find for sulfur dioxide. So answer is second option, that is 17 grams of ammonia. Next question number 3, model number 3. Calculate the number of moles occupied by 88 grams of carbon dioxide gas at STP. So this is very simple. So calculate the number of moles occupied by 88 grams of carbon dioxide gas at STP. Already we know 1 mole of carbon dioxide. Answer I'm doing it here now. Directly options I'm not giving, directly answer. Solution. So 1 mole of carbon dioxide contains 44 grams. 1 mole of carbon dioxide contains 44 grams. So 88 grams is equal to how much? Because the given weight is 88 grams. So simply you can say 88 divided by 44. So it is equal to 2 moles. So this is a question related to weight with respect to number of moles. Next question, weight with respect to volume. Question number 4. Same question they can ask like this also. Calculate the volume occupied by calculate the volume occupied by 100 grams of carbon dioxide gas at STP. At STP is important. If they are didn't specify STP, we cannot apply mole concept. So for every question they have to specify STP if you give in case of volume calculation. So already you know. Next solution for this, we know that 1 mole of carbon dioxide contains 44 grams. So directly we are giving here mole. 1 mole of carbon dioxide contains 44 grams. So it occupies how much volume? 22.4 liters is equal to 22.4 liters. So straight away I'm linking weight to volume. So here 100 grams occupies how much volume? So the relation is 1 mole of carbon dioxide occupies 44 grams, contains 44 grams and occupies 22.4 liters at STP. So 44 grams is occupying 22.4. Now, no need of considering mole here. Straight away we consider weight to volume. So 44 grams in this case, 44 grams is 22.4 liters. So given weight is 100 grams is equal to how much? So 100 into 22.4 by 44, that is equal to 100 into 22.4 divided by 44. So you'll get the answer. So answer you can write here easily. That calculation part I'm not doing because you know how to calculate. So this is the second model. So this is respect to weight with respect to volume of a gas, same gas. So calculate the volume occupied by 100 grams of carbon dioxide gas at STP. So weight with respect to volume. So X is equal to 122.4 divided by 44. You'll get the answer. Next question. Model number 5. All these mole concept problems are very, very important. If you know mole concept perfectly, you can do any problem in stoichiometric. Question number 5. How many moles are present in how many moles are present in 108 grams of are present in 108 grams of glucose. 108 grams of glucose. So this is the question. How many moles are present in 108 grams of glucose? So they are given to find number of moles by giving weight. So weight to number of moles. First, we should know the formula of glucose, that is C6H12O6. The formula of glucose is C6H12O6. Now calculate molecular weight of glucose. Molecular weight of glucose is equal to 6 into 12 plus 1 into 2, 1 into 12 plus 16 into 6. So 6 into 12, how it came? Because it has 6 carbon atoms and one carbon atom, each carbon atom mass is 12 grams. And hydrogen, each hydrogen atom mass is 1. And it is, how many are there? 12 are there. Since similarly oxygen, 16 oxygens, 16 is a atomic weight of oxygen, and we have 6 oxygens. And by totaling, we got it as 180. Now we can write next line, 1 mole of glucose, 1 mole of glucose contains 180 grams. Now given weight is how much? 108 grams. How much? So 108 divided by 180, which is equal to 0.6. So how many number of moles are present in 108 grams of glucose? 0.6 moles. So this is another model. Now next question. Next question. How many atoms are present in how many atoms are present in 1 ml of helium gas? 1 ml of helium gas. You can say 1 ml or 1 cc, both are same. 1 ml of helium gas. Helium gas at STP. So they are asking, this question is related to volume with respect to number of atoms. So first we'll write for general configuration, that is at STP, solution I'm writing here, at STP, 22,400 ml of helium contains is equal to Avogadro number of atoms, 6.023. Avogadro number of atoms, that is 6.023 into 10 to the power of 23. Now this is that link directly, we can get it from mole concept. So that is volume to number of particles. So 1 mole can occupies 22.4 liters at STP. So since the numerical they are given in mls, so I have converted the given liters into mls. That is 22.4 liters can be changed as 22,400 ml of helium. So 22.4 liters can be taken as 22,400 ml of helium. So it occupies straight away number of Avogadro number, because already we know 1 mole of any gas contains Avogadro number of particles. So here Avogadro number of atoms, that is 6.023 10 to the power of 23. Now we need to calculate in 1 ml how much. Next line, 1 ml how much. So we can write it as x is equal to 6.023 10 to the power of 23 divided by 2.24 in 10 to the power of 4. 2.24 in 10 to the power of 4 I have written, or 20,400. So answer you will get it as 2.69 in 10 to the power of 19 atoms. 2.69 in 10 to the power of 19 into 10 to the power of 19 atoms. After calculation, you can verify that calculation easily. This 22,400 we can write it as 2.24 in 10 to the power of 4. Because if you convert them in tens powers, it is easy for calculating. This 10 power 4 going to numerator becomes 10 to the power of minus 4. So 23 minus 4 is 19. So we got the answer 10 to the power of 19 like this. And 6.023 by 2.24 becomes 2.69 approximately. So the answer is 2.69 10 to the power of 19 atoms. So this is question number 6. Next question number 7. How many moles of oxygen atoms? How many moles of oxygen atoms are present in oxygen atoms are present in 75 grams of pure calcium carbonate? So 75 grams of pure calcium carbonate. This is very, very important question. How many moles of oxygen atoms are present in 75 grams of pure calcium carbonate? So first we have to calculate the molecular weight of calcium carbonate. CaCO3. CaCO3 equal to calcium is 40 plus carbon is 12 plus oxygen is 16 into 3, 48. So you'll get it as 100. So we know 100 grams of calcium carbonate is 1 mole. 100 grams of calcium carbonate is equal to 3 moles of oxygen atoms. 100 grams of calcium carbonate contains 3 moles of oxygen atoms because in calcium carbonate we have 3 oxygen atoms. So 100 grams is 1 mole. 1 mole of calcium carbonate contains 3 moles of oxygen atoms. So 75 grams contains how much? 75 grams contains how much? So 75 into 3 by 100 divided by 100. You'll get the answer as 2.25 moles. So this is a model with respect to number of moles as well as with respect to weight. So this model is also very important. So how many moles of oxygen atoms are present in 75 grams of pure calcium carbonate? If they are given, instead of pure calcium carbonate, if they are given 20% pure calcium carbonate, means we have to take into 20 by 100. Into 20 by 100. That type of questions you will get in next level. So now this is question number 7. Next model. Calculate the mass of 1 mole of electrons. We have to calculate the mass of 1 mole of electrons. 1 mole of electrons means it contains Avogadro number of electrons. So 1 mole of electrons. So answer for this, mass of each electron. Mass of 1 electron is equal to, in the solution, mass of 1 electron is equal to 9.1 in 10 to the power minus 31 grams. Or you can say 9.1 10 to the power minus 28 kgs. So straight away we can write mass of 1 electron is 9.1 10 to the power minus 31 grams. So next line. So for one electron we have this much mass. So 1 mole of electrons. So mass of 1 mole of electrons is equal to, next line, mass of 1 mole of electrons is equal to, mass of 1 mole of electrons is equal to mass of electrons into Avogadro number. Mass of 1 electron into Avogadro number, because we know for 1 mole of electrons we have Avogadro number of electrons. So that is equal to 9.1 10 to the power minus 31 into 6.023 in 10 to the power of 23. So approximately we got it as 5.5 in 10 to the power minus 7 kgs. 10 to the power minus 7 kg. I have converted that into kg. Or you can write 0.55 milligrams. 0.55 milligrams. We can convert the kgs into milligrams and you will get the answer 0.55. So this is the calculation for finding mass of 1 mole of electrons. Next. Calculate. Next question. Calculate the density of carbonized gas at STP. It's right question. They will not give any value. Just simply they'll ask calculate the density of carbon dioxide gas at STP. So at STP, uh, mass of carbon dioxide is 22 grams, no, 44 grams. At STP, we know mass of carbon dioxide gas is 44 grams. And it occupies 22.4 liters. Volume is equal to 22.4 liters. So we know the volume as well as mass. So density is equal to mass by volume. Density is equal to mass by volume. So we can write 44 by 22.4. So answer will come up to 1.96 grams per liter. 1.96 grams per liter. Because the mass we are taking in grams per liter, L minus 1. So in this way, you'll get the answer. So calculate the density of carbon dioxide gas at STP is 1.96 grams per liter. So this is the answer. So like these simple questions, they'll ask for mole concept. Next question. How many gram atoms? How many gram atoms are present in 4,000 AMU of calcium? 4,000 AMU of calcium. So this is atomic mass unit. AMU is given. So this like this also they'll give. So 4,000. We know that 4,000 AMU of calcium is equal to, doing the solution, 4,000 AMU of calcium is equal to 40 into 10 to the power of 2 into 1.66 in 10 to the power of minus 24 grams. So what is this called? We know calcium atom contains, the mass of calcium atom is 40 and 4,000 means 40 into 10 to the power of 2 because we have made 4,000 into 40 into 10 to the power of 2 and mass of each proton is 1.66 in 10 to the power of minus 24 grams. So 4,000 AMU of calcium is equal to 40 into 10 to the power of 2 into 1.66 in 10 to the power of minus 24 grams. So now 1 gram atom of calcium is equal to, next step, we have to find how many gram atoms. 1 gram atom of calcium is equal to 1 gram atom of calcium is equal to 40 grams. So number of gram atoms of calcium. So our question, our answer is what? Next line. Number of gram atoms of calcium in 4,000 AMU is equal to, in 4,000 AMU is equal to 40 into 1.66 10 to the power of 2 10 to the power of minus 24 into 10 to the power of 2 divided by 40 divided by 40 because we have to find number of gram atoms in 4,000 AMU of calcium. So by 40 because 1 gram atom of calcium is equal to 40 grams. So 4,000 AMU is equal to 40 into 1.6 10 to the power of minus 24 and 10 to the power of 2 by 40. The answer is 1.66 in 10 to the power of minus 22. This model is most important. So the answer is 1.66 in 10 to the power of minus 22 gram atoms are present in 4,000 AMU of calcium. So next question. Calculate, question number 10. Calculate The effective molecular weight of air. The effective molecular weight of air. AIR, air. Molecular weight of air. AIR. Now, answer. So before going to answer this question mark. So answer. Before going to answer, I'll tell you. Already you know air is a mixture of gases. So air is a mixture of gases. It contains nitrogen, oxygen, as well as carbon dioxide. So mainly nitrogen and oxygen as the main component. So remaining components will not take into consideration. So nitrogen and oxygen, we know air is a homogeneous mixture. It contains 79% nitrogen by volume, 79% nitrogen by volume, 78% nitrogen by volume, and 21% oxygen by volume. 21% by oxygen by volume. %, oxygen by volume. So the weight of 1 mole of air is equal to the weight of 1 mole of air is equal to 0.79 into 28, because the atomic weight of nitrogen is 28, and plus 0.21 into 32, because oxygen molecular weight you have to take 0.21 into 32. So after calculation, we will get the answer 28.84. 28.84. So in this way, we'll find effective weight, molecular weight of air. How you got this? Again, I'm repeating: 17% nitrogen by volume, 21% oxygen by volume, because air is a homogeneous mixture of gases, that is nitrogen and oxygen. So 17%, 21% oxygen by volume. So the weight of 1 mole of air is equal to 0.79 into 28. How you got 0.79? Because 79 by 1000 and 0.79, 21 by 1000, 0.21. So 0.79 percentage we are converting into volume. So 0.7 into 28 plus 32, 0.21 into 32. So it is equal to 28.84 grams. So these are the 10 important models of mole concept. And more about mole concept, we can find it in exercises. So mole concept, we have only mole concept we have completed right now. Next we do mole concept with respect to stoichiometric calculations. So next mole concept. Next mole concept. Mole concept with respect to stoichiometric calculations. Mole concept with respect to stoichiometric calculations. So what is mole concept with respect to stoichiometric calculations? So we are applying mole concept for chemical equations. In this case, we have to write the balanced chemical equations. Balanced chemical equations. So what is mole concept with respect to stoichiometric calculations? I'll just explain you that concept. Mole concept with respect to stoichiometric calculations. Consider a chemical equation. Consider a chemical equation. Chemical equation. So A moles of A moles of A moles of A plus B moles of B. Just writing in the equation pattern. Just see here. A moles of A plus B moles of B gives rise to C moles of C plus D moles of D. So this is a balanced chemical equation in which A and B are represented as reactants and C and D are capital C, capital D are products. Where small a, small b are number of moles of A and number of moles of B respectively, and small c, small d are number of moles of C and number of moles of D respectively. Now applying mole concept to this, for example, we can write a balanced chemical equations following the relative number of moles. The relative number of moles are molecules of the reactants and products. The relative number of moles are molecules of reactants and products are important here. Of molecules and products of reactants and products are important. Of reactants as well as products, I forgot to add the reactants and products are important. So how to apply mole concept for this, we are going to discuss, that is stoichiometric equations. Mole concept with respect to stoichiometric calculations. So how to apply concept? For example, consider one equation. I'll tell you in manner direct equation. C plus O2 gives rise to carbon dioxide gas. C plus O2 gives rise to carbon dioxide gas. We can apply mole concept for this equation. 12 grams of carbon, writing here, 12 grams of carbon combines with 32 grams of oxygen and gives 44 grams of carbon dioxide gas. So this is called weight relationship for reactants and products, weight relationship. So in this case, we have three models. So one is weight relationship. For calculations regarding stoichiometric calculations, we have three important models. Weight relationship, stoichiometric calculations. We have three important models mainly. Weight relationship, weight relationship, weight volume relationship, and volume relationship. So what is weight relationship? Here the weight of reactant is to be compared with weight of product. So they'll give weight of reactant at STP, or they'll ask us to find weight of product at the STP, same conditions. Or they'll give weight of product and they ask us to find the weight of reactant. Similarly, in the second case, they'll give weight of the reactant in the chemical equation, or sometimes they'll not give equation also, and they ask us to find volume of the product. Similarly, volume and volume also the same. They'll give volume of the reactant, they ask us to find volume of the product. So this is called stoichiometric calculations. Now we are going in detail with all these numericals. That is weight relationship. Now first, I'll give three examples in all the cases. First one, weight relationship. Weight relationship. Problems based on weight relationship we are discussing right now. Question number one. Calculate the weight of calcium oxide. Calculate the weight of calcium oxide obtained, calcium oxide CaO, obtained when 1 kg of calcium carbonate 1 kg of calcium carbonate is heated strongly. Is heated strongly. So they'll give a question like this, simple question. Calculate the weight of calcium oxide obtained when 1 kg of calcium carbonate is heated strongly. 1 kg of calcium carbonate is heated strongly. Now, how to find solution for this? For this, first we need to, when they have given the, if they have given the equation, we can straight away write the answer. But in this case, they have not provided the stoichiometric equation. First, for this question, we have to write balanced chemical equation of what happens when calcium carbonate is burnt. So, when heated strongly. So, calcium carbonate CaCO3 on heating forms CaO plus CO2. So this is the actual equation. Now we have to check whether it is balanced or not. So already it is balanced. So calcium carbonate, we have to write first, if they have not given the equation for this type of numericals, we have to first write the balanced stoichiometric chemical equation. Now this is a balanced stoichiometric chemical equation, that is calcium carbonate give on heating gives calcium oxide plus carbon dioxide. Now since they have compared weight, we are doing weight relationship. Now we can write the weight. We know from the equation 1 mole of calcium carbonate is 100 grams. 100 grams of calcium carbonate is giving 56 grams of calcium oxide, because calcium is 40 plus oxygen 60, and 44 grams of carbon dioxide. Now they have not mentioned about carbon dioxide, straight away they mentioned about only calcium oxide. So 100 grams is giving 56 grams. 1 kg means how much? 1000 grams. 1000 grams gives how much? 1000 grams gives how much? That is equal to 560 grams. So answer is 560 grams. So when 1 kg of calcium carbonate is heated strongly, it will give 560 grams of calcium oxide. So this is the example for weight relationship. They will give weight of reactant, they ask us to find weight of product. Sometimes they will give weight of product, they ask us to find weight of reactant. Now let us see that condition also. Question number 2. Question number 2. How many grams of sulfur dioxide? How many grams of sulfur dioxide is to be burnt? How many grams of sulfur dioxide is to be burnt? How many grams of sulfur dioxide is to be burnt to produce 160 grams of sulfur trioxide. 160 grams of sulfur trioxide, SO3. So at STP. This is the question. So for this also they have not given the equation. They have given the quantity of product, and we need to find the quantity of reactant. So for this question, see, first write this balanced stoichiometric equation. SO2 plus O2. SO2 plus O2 gives rise to SO3. So for this balanced equation, we have to write 2SO2 plus O2 gives rise to 2SO3. This is a balanced equation. Now from the equation, we can say 2 moles of sulfur dioxide is giving 2 moles of sulfur trioxide and burning with 1 mole of oxygen gas. So now write the sulfur dioxide weight is how much? So sulfur dioxide weight is 64. So 2 into 64 grams. 2 into 64 grams gives 2 into 80 grams. Because sulfur is 32, oxygen is 16. So we'll get sulfur dioxide weight is 80. So see, 2 into 64 grams gives 2 into 80 grams. So 2 into 64 is equal to how much? 2 into 64 is 128 grams. By this you can write 128 grams of sulfur dioxide 128 grams of sulfur trioxide gives 160 grams of sulfur trioxide. Straight away we got the answer. That is 2 moles is getting 2 moles. So we got 160 to produce 160 grams of sulfur dioxide STP. We require sulfur dioxide. How many grams? 128 grams of sulfur dioxide. So this is called weight-weight relationship. Next question. Same weight-weight relationship. What weight of magnesium oxide? What weight of magnesium oxide is obtained? What weight of magnesium oxide is obtained by complete combustion of 2 grams of magnesium. 2 grams of magnesium. 2 grams of magnesium by the complete combustion of 2 grams of magnesium. So first, again for this also we have to write the balanced chemical equation. So magnesium when burnt in oxygen it forms magnesium oxide. That is magnesium oxide is formed. So Mg 2Mg plus O2 gives rise to 2Mg plus O2 gives rise to 2MgO. So we know magnesium weight is 24. So 2 into 24, magnesium weight is 24. So 2 into 24 gives 2 into magnesium oxide is 24, oxygen 60, 40. 2 into 40. 2 into 40 grams. Now, so 48 grams is giving 40 grams of magnesium oxide. 48 grams of magnesium gives 48 grams, 80 grams of magnesium oxide. So 40 grams of magnesium gives 80 grams of magnesium oxide. So 2 grams gives how much? 2 grams gives how much? So answer is 3.33 grams. 3.33 grams. 160 by 48 into 2. So 3.33 grams you'll get answer. 2 into 80 by 48. So 160 by 48 you'll get 3.33 grams. Next. Now in this way we'll do weight-weight relationship. Now we'll do weight-volume relationship. Weight-volume relationship. Weight-volume relationship. When one or more of the reactants or products of the reaction are present in gaseous state, this method is applied. When one or more of the reactant or products of the reactants are present in gaseous state, of the reaction is present in gaseous state, this method is applied. And by saying the question, we can say they have given weight and volume. So in this case, what they'll give, to be simple, in this case, they'll give weight of reactant or volume of the reactant, and they ask us to find the weight of product or volume of the product. So this is called weight-volume relationship. Weight-volume relationship. Now consider in this case, question number 1. When 50 grams of sulfur, is burnt in air, at STP, what volume of sulfur dioxide gas is formed? What volume of sulfur dioxide gas is formed? Here in air or oxygen they will say. So here I'm taking air or oxygen, except air means we have to take air or oxygen. So when 50 grams of sulfur is burnt in air at STP, what volume of sulfur dioxide gas is formed? So solution for this is, first you have to write same here also balanced stoichiometric equation. S plus O2 gives rise to SO2. So here in the previous questions we have done weight of reactant, weight of product. But here we have to take weight of reactant is given, volume of product we have to compare. We have to compare by using mole concept. So from this equation, you can say 1 mole of sulfur on burning with 1 mole of oxygen gas, it forms 1 mole of sulfur dioxide gas. So already it is balanced. So 1 mole of sulfur contains how many grams? 32 grams. 32 grams of sulfur gives 1 mole of sulfur dioxide, means it occupies 1 mole of any gas at STP occupies how much? It is 22.4 liters. So 32 grams of sulfur gives 22.4 liters of sulfur dioxide at STP. So now the given weight is how much? 50 grams. 50 grams how much? So 50 into 22.4 by 32. 50 into 22.4 divided by 32. You can calculate that answer. So in this way you have to solve it. So this is called weight volume relationship. Weight volume relationship. Weight volume relationship. Question number 1 is over. Next, weight volume relationship. Question number 2. What volume of hydrogen gas at STP is required to reduce 7.95 grams of cupric oxide, 7.95 grams of cupric oxide CuO to give copper metal. So they're asking us to find what volume of hydrogen gas should be required. So to produce copper from hydrogen. So we can write CuO plus H2. For this the equation CuO plus H2 gives H2, Cu plus H2O. Cu plus H2O. So we can see 1 mole of cupric oxide on reaction with hydrogen, 1 mole of hydrogen gas at STP gives 1 mole of copper and 1 mole of water gas. So 1 mole of water, not water gas, simply 1 mole of water. So by this you can write 1 mole of cupric oxide is equal to 1 mole of hydrogen gas. So we can write what is the weight of, first we have to calculate cupric oxide weight, that is copper is 63.5 plus oxygen is 16. So it is coming around 79.5. 79.5 grams of cuprous oxide. 79.5 grams of cuprous oxide will combine with 1 mole of hydrogen gas. So any 1 mole of any gas at HPA occupies 22.4 liters. So we can say 79.5 grams of cuprous oxide will combine with 22.4 liters of hydrogen gas. Will combine with 22.4 liters of. So I'm writing here the reactant itself, 22.4 liters of hydrogen gas. So here they are asking weight of reactant of one reactant with respect to weight of another reactant only. They are not asking anything about product. So what volume of hydrogen gas at STP is required to reduce 7.95 grams of cuprous oxide to give copper metal? So they are comparing with cuprous oxide with respect to hydrogen, and based on mole concept we can see cuprous oxide molecular weight is 79.5 grams. So 79.5 grams is combining with 22.4 liters. So 7.95 grams combines with how many liters? So simple, it is 7.95 into 22.4, 7.95 into 22.4 divided by 79.5. It comes around 2.24. So the answer is 2.24 liters. So this is called second model in weight volume relationship. Next, third model in weight volume relationship. Next, third one. 6 grams of magnesite mineral. 6 grams of magnesite mineral on heating liberates carbon dioxide gas lipids, carbon dioxide gas, which measures 1.12 liters at STP, which measures 1.12 liters at STP. What is the percentage purity of mineral? What is the percentage purity of the mineral? Percentage purity. This is very, very important model. Percentage purity of the mineral. So before going to solution, let me tell you, magnesite means magnesium carbonate. So magnesium carbonate on heating liberates carbon dioxide gas. Already we know that. So the equation first we have to write again here the balanced chemical equation, that is MgCO3 gives rise to MgO plus CO2, MgO plus CO2, magnesium capital. So already writing here MgO plus CO2. So magnesium carbonate on heating forms magnesium oxide plus carbon dioxide. Now comparing to stoichiometric calculation, magnesium weight is 24 plus 12 plus 48. So 24 is magnesium, carbon is 12 plus oxygen is 16. So 24 plus 12 plus 48. From this we can write weight of magnesium carbonate is 1 mole of magnesium carbonate is 24 plus 12, 36 plus 48 is equal to 84. So 84 grams of magnesium carbonate gives 22.4 liters of carbon dioxide gas. 22.4 liters of carbon dioxide gas. This is the generalized equation. Now 6 grams gives how much? Because they have given 6 grams. But we should not write 1.12 liters. Just we have to see 6 grams gives how much. So 6 into 22.4. 6 into 22.4 divided by 84. So which is coming around 1.6 grams. 1.6 liters, sorry, 1.6 liters. So when 6 grams of magnesium, pure magnesite mineral is heated, we should get 1.6 liters of carbon dioxide gas at STP. But unfortunately, we got only 1.12 liters. So only 1.12 liters of carbon dioxide gas is obtained at STP. So some magnesium is a magnesite mineral is not 100% pure. So the weight of impure magnesium is equal to, the weight of pure magnesium carbonate to be decomposed is equal to the weight of magnesium carbonate to be decomposed is equal to the weight of magnesium carbonate to be decomposed is equal to 1.12 by 22.4 into 84, which is equal to 4.2 grams. So here you can see this step. Weight of pure magnesium carbonate to be decomposed to produce 1.12 liters is 4.2 grams. But actually we have taken 6 grams. So percentage of purity is equal to percentage of purity is equal to 4.2 divided by total weight, that is 6 into 100, which is coming around 70%. So this question is very, very important for high level exams, all competitive exams, JEE mains and JEE advanced or NEET. So simple, again I explain the problem. If you want to understand clearly, you can understand. 6 grams of magnesite mineral on heating liberates carbon dioxide gas, which measures 1.12 liters at STP. And what is the percentage of purity of the mineral? So by this question, we can understand 6 grams of magnesite mineral is being heated, and we are getting only 1.12 liters of carbon dioxide gas at STP. Now from the stoichiometric equation, we can write MgCO3 gives us to MgO plus CO2. So 84 grams gives 22.4 liters of carbon dioxide gas from the stoichiometric calculation by using the relation weight to volume relationship. So 84 grams is the molecular weight of magnesium carbonate and 84 grams 1 mole is giving 1 mole of carbon dioxide, that is 22.4 liters of carbon dioxide. So 6 grams gives how much? Actually, it should give 1.6 liters, but unfortunately, it has given only 1.12 liters. So magnesite mineral is not 100% pure. So to know the impurity of magnesite mineral, we should know the actual pure magnesite mineral to be decomposed to give 1.12 liters of carbon dioxide gas. So that can be calculated 1.12 by 22.4 into 84, which you are going to get around 4.2 grams. So to produce 1.12 liters, we require only 4.2 grams of pure magnesium carbonate. But we have taken 6 grams of magnesium carbonate. So to find percentage of purity, 4.2 by 6 into 100, yes, it is 70%. So this is the answer. So in this way, we have to calculate. So these are the 3 important models based on weight, volume, relationship. Next, we will discuss weight relationship. Weight, volume relationship. Volume relationship. We have completed weight, volume. Now final one, volume relationship. So volume relationship. In this type of questions, they'll give volume of the reactant as well as volume of the product. They ask us to find any one of these at STP standard conditions. So volume of the reactant or volume of the product, they ask us to find. So question number 1. This is based upon Gay-Lussac's law. Very important. Based on Gay-Lussac's law. What is Gay-Lussac's law? Equal volume of all gases at STP contains equal number of, write down Gay-Lussac's law, equal volumes So no need to apply directly, you can compare in volumes. Equal volumes of all gases at STP contains equal number of moles. Equal volumes of all gases at STP contains equal number of moles. So this is called Gay-Lussac's law. That is simple. Volume is proportional to number of moles. That is V is proportional to N. V is proportional to N. So as the volume increases, number of moles also increases. So no need to apply mole concept directly. In case of volumes, you can convert directly. Means here, what I'm trying to say, in case of volume relationship, when you are comparing with volumes and number of moles, straight away we can compare directly. For example, H2 plus Cl2 gives 2HCl. So in this case, directly you can say 1 mole of hydrogen gas combines with 1 mole of chlorine gas to form 2 moles of HCl gas. Simply, we can say here also, since volume is proportional to number of moles, so 1 volume of hydrogen gas combines with 1 volume of chlorine gas to form 2 volumes of hydrogen chloride gas. So this is the direct relationship for volume, because since volume is proportional to number of moles, so for volume we can take direct relationship directly. No need to take weights also, no need to take number of moles also. By seeing the stoichiometric equation, we can find out. So now let us see the problems based on this volume relationship. Question number 1. What is the minimum volume of carbon monoxide? What is the minimum volume of carbon monoxide? Minimum volume of carbon monoxide, that is CO, at STP needed to react completely with 0.112 liters, to react completely with 0.112 liters of oxygen gas at STP. So this is the question. What is the minimum volume of carbon monoxide at STP needed to react completely with 0.112 liters of oxygen gas at STP? So here minimum volume is not required. Just I'm rubbing minimum volume because it will make confusion. So what is the volume of carbon monoxide at STP needed? So what is the volume of carbon monoxide at STP needed to react completely with 0.112 liters of oxygen gas at STP? So for this question, simply write the equation 2CO plus O2 gives us to We are writing the balanced chemical equation. 2CO plus O2 gives us 2CO2. So from this we can say simply 2 volumes of carbon monoxide combined with 1 volume of oxygen gas. So by this you can see they are in the ratio of 2 volumes and 1 volume. Means that is 2 volume means 2 ml or 2 liters. For to react with 1 liter of oxygen we require at least 2 liters of carbon monoxide. Just next step you can write 2 liters of 1 liter of oxygen gas. 1 liter. So here we are getting 2 liters. So to react with 1 liter of oxygen gas, we require 2 liters of carbon monoxide gas to produce carbon dioxide gas. So we can say 0.1112 liters of oxygen. 0.112 is how much? So it is equal to 0.112 into 2 divided by 1. 0.112 into 2 divided by 1. So which is equal to 0.224. So 0.224 of oxygen gas, carbon monoxide, 0.224 liters of carbon monoxide is required to produce, is required to react with 0.112 liters of oxygen gas for the reaction. So this is the question number 1. Next question number 2. Question number 2. Calculate the volume of carbon dioxide gas obtained. Calculate the volume of carbon dioxide gas obtained when 10 ml of acetylene, 10 ml of acetylene gas is burnt in air. 10 ml of acetylene gas is burnt in air at STP. So they are given 10 ml of acetylene gas only. They are asking us to find volume of carbon dioxide gas obtained. So we know acetylene formula is C2H4. C2H4 plus O2 gives H2. CO2 plus H2O. Because any organic compound when burns in air or oxygen forms carbon dioxide and water as the only product. Again, a repeating statement. Any organic compound or any hydrocarbon when burnt in air or oxygen forms carbon dioxide and oxygen water as the only product. So now we have to do balancing. That is C2H4 plus 2O2 gives H2. 2CO2 plus H2O. C2H4 plus 3O2 gives H2. 2CO2 plus 2H2O is the balanced stoichiometric equation. 1 mole of acetylene combines with 3 moles of oxygen gas to form 2 moles of carbon dioxide gas and 2 moles of water. So in this way, we can say 1 volume of acetylene gives 2 volumes of carbon dioxide. So 1 ml of acetylene, 1 volume gives 2 volumes of carbon dioxide gas. So it is nothing but what? So 1 ml gives 2 ml. So from the equation, we can say 1 mole of acetylene gives 2 moles of carbon dioxide. So 1 volume of acetylene gives 2 moles of carbon dioxide. So 1 ml of acetylene gives 2 ml of carbon dioxide. So 10 ml gives how much? So it is equal to 20. So this is the model number 2. Next, question number 3. Same question, they'll ask in different manner. Calculate the volume of oxygen required. Calculate the volume of oxygen required for the complete combustion of 10 liters of ethylene, 10 liters of ethylene gas, ethylene gas, ETHYLEN, ethylene gas under similar conditions. So for this again we have to write the balanced chemical equation, that is C2H4 plus 3O2 gives rise to 2CO2 plus 2H2. So from the equation we can say here we have to compare only reactant and reactant because they are comparing with oxygen and ethylene gas. So 1 mole of ethylene, so 1 volume combines with 3 volumes of oxygen gas. So 10 liters gives how much liters? So it is equal to 30 liters. 30 liters of oxygen gas is required for the complete combustion of 10 liters of ethylene gas under similar conditions. So in this way we have to do weight relationship, weight volume, and volume relationship. Next very important factor. Next one more question I'll do. Last question in this session. Question number, write down question now. What is the volume of carbon dioxide obtained? What is the volume of carbon dioxide obtained under similar conditions when under similar conditions when 30 ml of mixture of methane and ethane, 30 ml of mixture of methane and ethane in the ratio X is to Y, methane and ethane, CH4 and C2H6, CH4 and C2H6 in the ratio X is to Y. The ratio X is to Y gives 40 ml of carbon dioxide. If 30 ml of the mixture is taken in Y/X ratio, if 30 ml of mixture is taken in Y/X ratio, question mark. Now here you see. So in the first instance, when 30 ml of mixture of methane and ethane in the ratio of X is to Y gives 40 ml of carbon dioxide. Now they're asking if 30 ml of the mixture is taken in Y/X ratio, that is ethane and methane, what is the volume of carbon dioxide obtained? So for this case, we have to write the two equations, that is methane and ethane on burning. So first CH4 plus O2 gives rise to CO2 plus 2H2O. Next ethane C2H6 plus O2, C2H6 plus O2. So if I'm writing ethane also, C2H6 plus O2 gives rise to 2CO2 plus 3H2O. So for oxygens here, 4 plus is 7O2, 7 by 2O2, you can write 7O2. And for here, oxygens will be 2O2. So oxygens is not required here because we have to take X is to Y for ethane and methane. Now from this equation, we can say 1 volume of methane combines with to give 1 volume of carbon dioxide in the first case, and second case 1 volume of ethane gives 2 volumes of carbon dioxide. So 1 volume gives 1 volume of carbon dioxide, and here it is giving 2 volumes. But as you can say, x plus y is equal to 30. X plus y is equal to 30 in the first case, and x plus 2y is equal to 40 because it is giving 2 volumes, so 40. How we got this? Because they are giving 30 ml of each. So 30 ml means x plus y is equal to 30. Second is x by 2y is equal to 40. By solving this, y is equal to 10. Y is equal to 10. So x is equal to 20. X is equal to 20. So if you take 20 ml of methane and 10 ml of ethane, we get 30 ml of carbon dioxide. Now, if the ratio is reverse, that is in the case of x is to y. Now, if the ratio is reverse, that is y is to x, that is 10 ml of methane and 20 ml of ethane. So y is to x. So we can say 20 ml of methane. So we'll get 10 plus 40, 50 ml of carbon dioxide gas. So again, I'm writing here, if y ml of methane is taken, if y ml of methane, CH4 is taken, we'll get y is equal to 10. Y is equal to 10 because it is 1 mole. And XML of ethane, XML of ethane, XML of ethane C2H6. Since ethane, for the equation, we can say it is required 2 moles of carbon dioxide. So XML is 20. So 20 into 2, it is 40. 20 into 2, it is 40. So by this, you can say 10 ml of Y and 40 ml of X. So 50 ml of carbon dioxide is formed. How much is formed? 50 ml of carbon dioxide is formed. 50 ml of carbon dioxide is formed in the second case, that is Y is to X. So this is the answer. So this is the answer. So I'm ending the class session today, and thank you all. Thank you all. So do the problems carefully as we have discussed.